We're filming?
We're filming.
I'm Thomas Brandt. This is Mae30a final review. Get ready. We got 20 chapters, lectures. This is lecture 1. We start out with mostly definitions of kind of what the class will look like and what do these words mean. Mechanics is just a study of behavior of physical bodies, subject to forces, and kind of how they interact, what they do to their environment. For statics, which is what this class is all about, it's an analysis of loads in physical systems in static equilibrium. This is important because that's how we can set net equations equal to 0 and start solving for stuff pretty easy. This is also intro to dynamics, and we'll do dynamics next quarter. That's just the study of bodies in motion. And then I'm sure later on we'll talk about kinematics and kinetics. Kinematics is geometry in motion, and kinetics is relative force on a body to mass and acceleration. Another important definition is particle versus rigid body. In this class, most of our problems actually just focused on particles, which it makes our lives a lot easier because size and shape is negligible, and we consider forces concurrent at a single point. So let's say this is kind of one point, this fish right here. A fish is kind of a complex geometry, but now we can simplify it, whereas with rigid body we need to consider, the fish has a big tail here, that's a different shape. So size and shape would have to be considered, and it complicates things. Next we have Newton's laws. I think he's the Apple guy. Maybe he's
the Apple guy.
Yeah, and he always has some crazy flow, and you look up a picture of him.
Kind of looks like you.
Some people do call me the modern day Newton. I'm just
okay.
I'm just saying. Did I make these laws? First, objects remain at rest or in constant velocity unless acted upon by an imbalanced force. It's like physics 101.
Oh.
Next, we got second law. Acceleration depends on mass and applied force, which is pretty much F equals ma. It's an important one. You should write that down. Third law, equal and opposite forces in direction of one body that applies the initial force. I try to write my own definition for that one, and it's confusing, but basically that's kind of where we get normal force. So this wall is exerting a normal force apt to my applied force. And then we also learn about, she talks about SI, units, metric, imperial. You'll be all right, you'll figure that out.
Yeah.
And then also there's prefixes, so there's a whole list. You don't need to know all that. You mostly just kilo and milli. You
it's
should
just little
probably know.
conversions.
That's 10 to the third, 10 to the negative third. And on the cheat sheet, she includes conversions, so should be good.
All
you
right.
got it, gang. Yeah. Lecture 2.
Let's find lecture 2.
Lecture 2.
There's Andrew. Here's Case. He's about to show us the second lecture. Say hi, Case.
I'm Case. I'll be doing lecture 2 right now.
All right.
Alright, here we have 2D particles. So 2D particles, we gotta know the difference. We've got to know the difference between a scalar and a vector. So scalars have magnitude, right? Something like mass.
Yeah.
Something like a force has a magnitude and a direction. Very important. You gotta know that. Speaking of forces though, we have the triangle parallelogram law. So you see there's 2 forces in a system, right?
I see him.
We can actually isolate them. We can create a parallelogram between them and draw a resultant force between the 2 forces, between that parallelogram, and actually create a triangle out of those 3 forces. And this law states that both forces add up to that resultant force. So with 2D particles, we actually express them in Cartesian coordinates in a Cartesian plane that contain ijk vectors, we call them. So let's say we have this xyz plane with this force A. It has xyz components. So we would write it in the x with the I force, I direction, the y force in the j direction, z force, k direction, right? So another important part of 2D particles is actually particle equilibrium, which states that net force is acting on a particle is 0, which is where we get the sum of the forces is 0. Very important in this class. That's the basis of this entire class. You gotta know that.
Okay.
I'm gonna quiz you at the end. Actually, they're like a little drawing, see, of the forces that act on a particle. And it contains all forces, known and unknown, and it's in a coordinate system. So we have the x and the y plane.
I'm ready for the quiz.
Okay. What is particle equilibrium?
It's when forces are equal, they sum up to 0?
You got it?
Oh.
On to the next one.
Okay,
All
okay.
right, so now we're going to move on to some 3D particles.
Oh, I gotta get
So-
the whole board in here.
When you're representing a 3D particle, typically you're going to be dealing with problems like this. You're going to have a particle and then a bunch of forces acting on it. If you remember a lot of those, we had like a plate was being held up by some like cables or something like that. So it's going to be a lot of those type of problems. So when you're looking at this is like midterm 1 content. There is 3 different ways that you can express your vector as. So typically the approach to the problem is going to be to take this particle and the forces acting on it and vectorize everything. So you're gonna put everything in vectors, and you can express this in 3 different ways. Number 1 is with a unit vector, which is what Case was just talking about. You can use Cartesian coordinates, ijk. The second way is spherical coordinates. So let's say we have this vector f right here. You can express its x, y, and z components, respectively. So we have the angle between the y-axis and the force, that's theta y. That's going to be equal, that's going to how we're going to express Fy. And then Fx and Fz are going to be used with this angle phi I've drawn right here, which is found using the projection of the vector onto the 2D xz plane. So we had to do this on the first midterm, I think, on a big problem. And then the last way you can represent them is the cosine angles. So respectively for x, y, and z, the force in that direction is equal to the total force times the cosine of the respective angle. And then they're going to give you a lot of different information, so on the problem you're going to want to put together this information to see what you can find out. So sometimes they might give you theta x, theta y, and then you can use that to find using the law of cosines to get your last angle. But that's typically going to be the approach to this problem. And it's also important to note how to find the magnitude. I think everybody knows this, but just to review it, you're just taking the square root of each component squared, and that's going to be your magnitude. So that's pretty much the approach for a 3D particle problem. And this is lecture 3. I think we're ready for lecture 4.
Alright, where's 4?
Lecture 5, actually.
Lecture 4 was like
Oh.
teaching that, so we're
Yeah.
gonna do
So,
four.
lecture 5.
I'm back. So we got moment. A very, very important concept in this class. It's the basis of everything. But before we start moments, we've got to know the difference between a particle and a rigid body. Thomas was talking about that earlier, but let me explain it in a bit more detail, a bit better.
Okay.
So we got particles here, right? It's like a system with, a hanging system with cables. We actually, we do not consider rotation. We could say it's in equilibrium. We can draw the FBD as a particle with all the forces acting on that particle. And with particles, the size and shape of it does not matter. And the equation we use for that, you remember this one? I was just talking about that.
Oh my god, is that
Zero.
that equilibrium equation?
That is correct. But now we have a second one for rigid bodies, right?
What's that M mean?
Let's get to that. It might have something to do with the moment, but we'll see. So rigid bodies actually do have a defined shape that matters, and we take that into account. And it has rotational motion. That rotational motion might have something to do with that delta M, or the sum of the M's. But first, before we get to that, the moment is the rotational effect of a force. That's what you're wondering. So external versus internal forces in a system. We have external forces such as like attention,
applied
like
force.
yeah. It's exactly it's a force that acts on the body from a separate body, while an internal force is
So
a
if I
force.
push you off that chair, I'm an external force.
That is true, but the internal force is like my weight.
Yeah.
Or my normal force is something like within me.
Okay.
So to calculate the moment, either we have
Well, wait, hold on. Can I have a question?
Yeah.
Your weight would technically be external, correct? But like maybe the force that like your arm puts on like your shoulder, that's internal.
I guess.
But like your
depends
weight,
how
if you're looking
specific
at
you
the
look
whole
at it.
body, yeah,
Yeah.
But I see what you're saying.
Yeah. So the moment part, the actual moment, is calculated by F times the perpendicular distance, such as this diagram. We have a moment about A, right? We have a force here, and the perpendicular distance to that A is the R. But let's say we have a force like this and multiple R's going off of that. We'd actually do R cross F. We gotta bring in the determinants now. And we can say that, remember this? Sum of the M's is 0?
Mm-hmm.
We're gonna bring that here. The sum of the M's is every single R cross F. So we got R1 cross F, we got R2 cross F, and R3 cross F. That's how you calculate it.
Thank you.
I'm taking a little journey over here.
Alright.
You thought moment was cool. What about moment about an axis? All right.
Oh, okay.
Let me show you. Step up on that chair.
Here's the
Don't
chair.
jump it.
Let me,
Dude, you want me to hold
let me make my way over. Actually, That's a bad idea.
No. We're not.
All right, we're gonna go up at the same time.
Uh-oh. Look at that. Look at that tracking shot. We got lecture 6 right here. Moment about an axis. Okay, so first it was like dot product review. We all know that. We all know that. It's like dot AB equals AB cosine. You got like if A dot B is equal to 0, perpendicular. But basically we're gonna use it to find angles between line vectors in space, line or vectors in space, and components of vectors parallel and perpendicular to a line. Here are some more laws that you should kind of know probably by now.
You coming over here?
Yeah, can you slide me over a little bit?
Oh.
We're good.
Good.
Yeah. Okay. Now we're really digging into the moment on a specified axis right here. So this is our basic equation. It's before when we use like magnitude of moment, it was just like r times f or whatever, or like perpendicular distance times the force.
Get closer.
Yeah.
Now we have to use cross product, which you should also probably know by now. And I have a little example here. It's really hard to draw, but this is like it's like a hatch.
hinge. Okay, yeah,
But
yeah.
then there's 2 hinges here, so it goes like that actually. And basically,
Thomas, look. If you look right down here, I think you gotta look at
look at that applied example.
Look at this.
Oh my god.
Physics is
Let me
everywhere.
get a view of the hinges. Let me get in there.
So you can see it's able to rotate about this axis, but it can't rotate anywhere else. I can't rotate it like that.
And what Andrew's hands right now are doing is that's an applied force.
Okay. Let me just. Yeah, let me get it on that.
Do we need?
External force. Okay.
Love this application class. I think you guys will do very well
We're
on the
expending a
final.
lot of extra credit for that.
So, Brian, take notes. We got F is equal to 140 pounds. So that's our applied force. You can't really tell, but this is like, there's a rope here and it's being pulled. And I won't go through the whole thing, but some important things is we want to turn this into like a vector here. So we do that with, we're using RAB. I didn't put my points down. I'm trying to remember what AB actually was. But yeah, you have your AB vector, and then you put it over the magnitude, which is Pythagorean theorem. Someone, I think Case talked about it already. And yeah, eventually you're just going to turn it into this, which is just a dot product of this cross product. And then you should get a scalar value that's in pound, feet, or whatever units you're working with. You got that.
All right. I think we're gonna hand it over. All right. Lecture 7.
Big reveal. I'm also here. So I'm starting off with a short
Where,
one.
where am I looking?
Lecture 7 right here. it's a short and sweet one, don't worry. Basically, it's just the definition of a force couple. It's just 2 forces that are equal magnitude but opposite direction. So if I had a force going here that's like 50 newtons and a force going here 50 newtons, that's a force couple right there. So basically, there's a little definition for calculating them, the moments of a force couple. So if we have the position vector B, position vector A, and they're both being crossed by the force, but in opposite directions, all we have to do is factor out the radiuses and subtract them, and then we can just do the cross product like normal with the force, and you're done. That's all you gotta do.
That's beautiful.
Easy.
Pretty nice and simple. Nice and simple. Should we transition?
I knew you were missing me. Come on, bring it back. Lecture 8, talking about equivalent force. That is not the same as equilibrium. I want you to remember that, right? Right? We'll get there. It might be a quiz later. We got, so by definition, 2 systems of force couple moment are equivalent if they produce the same external forces, like Case was talking about. You can also consolidate forces and moments to a common point. So really quickly, here's like a diagram. You got a force going there. There's a moment. You can condense that, right? Boom, boom. You got a moment. You got
So
one
all of
force. It's
those
beautiful.
are now that.
That's easy to work with.
Okay.
As I touched on a second ago, it's not equilibrium problem. Do not set equation to 0. It's not the same thing for equivalent force.
not
And then this is a horrible drawing, but this was a grinder.
Help him move. Yeah.
That's good. That's good.
Are you good?
Yeah. So this is a grinder. We had a force being applied there. This is the components in the IJK format, and there's also a force here. And so we want to turn that into an equivalent force system. And really all it is like summing the forces here, and then for a moment we did have to do R cross F, and then adding those two R cross Fs to get the net, that net moment, and that's our...
Is this gonna be like the one that was on the multiple choice of midterm 2?
It might just be like the one midterm 2 multiple choice, which I know trips some people up, so study up. There you go.
Okay, thank you very much. All right, I think I'm gonna be up next. Somebody wants to take. There we go. There's lecture 9 and 10. Somebody else gonna. Somebody. Okay, thank you. All right, so now we're gonna be looking at rigid body equilibrium. We can set the equation to 0 now again. So our delta moment and delta F are both gonna be 0. And the key concept here is pretty much this one sentence is gonna sum up these 2 lectures. We're looking at 2D and 3D rigid body equilibrium problems. Basically, if you make a correct free body diagram, and assuming you know how to add numbers together and do some cross products, you're gonna get it right. The hardest part is the free body diagram. And with the free body diagram, all you have to do is add the forces in any direction that movement is restricted. So we have some examples, some 2D examples and a 3D example. And we're gonna be looking at where movement is restricted and where I'm gonna be adding forces and moments. So, if we look at this first one, this is a roller. So we have, it's like a beam on a roller. This is often used in bridges and whatnot. So because the movement is only restricted in this Y direction, we're only gonna have a force in the Y direction. The X direction, the beam is free to move horizontally, so we don't need a force there. So rather than there being a force, you can think about it as motion is carried out. So the force would be carried out into a motion rather than an applied force. So here, this is a hinge. So it's able to rotate. Also something I didn't say about this one is it can rotate, so it's on the ball. So that's why there's no moment, because like it's being carried out. So same here, it can rotate. So this beam is like kind of there. It can rotate, but it can't go side to side. So that's why, or up or down. So that's why we have an F and a Y. And here, if we just look at a fixed beam, this is like, imagine this is inside like a wall, inside a wall. So now that its movement is being restricted and it can't rotate, we're going to have an applied moment. And then if we look over here at this 3D example, this is kind of a rod you can think about, and there's a, I don't know what you would call that, a bearing around that. So it's like if this is my arm is the rod, it's gonna be around that like this. So it's gonna be restricting it. The rod can slide through, so that's why there's gonna be no force in this, would be the X direction, depending on how you look at it. And it can rotate, so we can twist it, can move my arm like this, I can move it like this, but I can't move it this way, I can't move it up. So that's why we're gonna have the applied force here, and same thing with the moment. If I tried to rotate this whole system that way, it's gonna cause a moment. And if I tried to rotate it this way, it's gonna cause a moment as well.
I think in some of the questions too, they'll specify in the
Yes, a lot of times they'll tell you if it's confusing, and you can obviously ask the TAs too a lot of times, like what type of like joint is this, or that type of thing. But the key is just add forces in any direction that movement is restricted. So this is 9 and 10.
Sweet.
I think we're ready for 11.
Let's bring it over here.
All right, you like bridges? You a fan of bridges?
Big fan
I'm
of
gonna
bridges.
teach you all about them.
Wow.
So basically, a bridge is formed up of trusses. What's a truss? It's just like a bunch of two-force members. This is what a two-force member is. Look at this. Bring it in. You got like this line here. You got this object, and you got these two forces on the ends of it. They can either be pulling apart or they can be pushing towards each other. They just have to be on the same line of action. They have to be opposite direction. They have to be equal magnitude. I want you to think back to what I was just telling you about force couples.
What you just tell me?
They're pretty similar, right? They're in opposite directions. You could assume these are the same magnitude, but look, there's this like, there's this separation between them.
Doing in there.
So that's basically the difference. Now let me walk you through my favorite way of finding the internal forces in a truss. It's called the method of sections. You got this bridge here. I drew this wonderful bridge for you. It's got all these points and these forces on it. We are going to start by drawing a free body diagram of the entire system so you can find the external forces on it. In this example, we have AY, AX, and BY along, or EY, along with all these forces acting on it up here. We can make a moment equation.
Wait, can I just point something out? I'm just gonna tie these 2 lectures together.
Let me. So,
if you notice right there, I was talking about a little nice little roller action. It's not drawn in this problem, but I think initially there's this part of the bridge is going to be on a roller. So you'll notice there's no EX or, so there is an AX. So this is on a joint most likely, and this is going to be a roller. So that's why there's no EX seen. Anyways, continue. Thank you.
That was perfect. Thank you. A little alley-oop. So we take that moment equation. The only unknown is EY. We solve for that. The reason that there's no AY or AX in this equation is because we're taking it from point A. So we can just ignore them essentially. They're gone. Then from there, we're gonna actually do our cut. That's what this line right here is. You can only cut through 3 members at the same time, 3 maximum. Then we're gonna make a new free body diagram replacing those cut members with internal forces. That's what we got here. Yeah, bring it in. And now we'll have our new forces along with, I'm sorry, I forgot to draw them, but we got this force here still along with EY. So from there we can draw an FX, or we can build an FX and FY equation. Set them equal
just like
to
right
0. Yeah, one right here and then up here. So in the X, in the X direction we'll have this. We can determine the angle, here would be a 4x4, so this would be a 45-degree angle. Basically put those equations together. If there's any other unknowns you need to find, you can just do another moment and cancel those out, and it just becomes an easier equation. Solve for something new.
Sweet. Thank you.
Oh, I'm still going.
Oh, he's moving. Look at him.
Well, let me get up here real
Give me a
quick.
chair.
I got you.
Please. Thank you.
All right.
Let me know if you need.
So now we're just advancing. It's the same stuff essentially. Now we're doing machines and frames. I just want to recap. So 2 force members, it's a structure entirely made of 2 force members, and it's always going to be stationary. It's not going to move. A frame is going to have, it's going to be partially made of 2 force members, but it's still going to be stationary, but it's just going to have like non-2 force members included. And then a machine will also have some 2 force members, but it's going to move. And so the process is a little different because we're not going to be cutting anything apart, but we will be taking it apart into the pieces where, pivot points where things can actually be separated physically. So this part's optional. I'm going to skip over that. First, we're going to make a FBD of just the external forces, the same way we did with this guy. So here we have the, what did you call those? Like right here where it's held in place. I forgot the word.
Oh, like it's just locked in there?
Yeah, what's the word for that? Joints. Yeah. So we got joints here.
Yeah.
So those will be external forces because they're preventing the object from moving. There are some in here, but they're internal because it's holding itself together. And then we'll have this external force. So you'll make force equations with that. You can do moments to find one of these unknowns. We'll also take a free body diagram of just this section. So like I said, you can take it apart into its individual pieces. So we'll take this crossbar here. You can do a moment of this too because P would be known. And you could essentially just, if you take the moment at B, you'd get rid of these and then you had equations for CX and CY, you could solve for those. And then by that point, you'd also found EY and EX from this first one. So you'd have this, and you could solve for AY and AX, and by then you'd have every single force or reaction.
Can I just add in, I think this was on the midterm, and I think this was actually the take-home part of, I think it was midterm 2, which is stumping us a little bit. It was a similar A-frame, similar to this.
Yeah.
And I think there was not a joint here. So like this problem, you can totally take it apart, but if it's like welded together, you can't take those 2 apart. So like in the midterm, it was like welded like this. So we couldn't split those apart because they're welded, so their forces are gonna be internal. But that's just something to keep in mind.
Yeah. Usually
Usually the problem will make that clear. You could probably ask the TA, but where there's joints, take it apart. But if it's welded
one
or like,
piece,
if
you
it's
can't.
one piece, yeah, don't be taking that apart.
All right.
Something to know.
Good stuff.
Get over here, Tom. Follow me.
Mr. Rowan. That's a Rowan.
You got a bit tired of Evan. He's been teaching a bit. You've been missing me. I know you've been
I
missing
know
me.
it. I know it.
We got friction here. It's kind of a short mini lesson. But
An
friction
upgrade from the crunch bar?
No, this little thing.
What is
It's actually, I don't know, I just found it. It's the force of resistance against the motion of an object, right? And it's given by mu, which is coefficient of friction times the normal force of an object. So we have static friction, which is before the object is moving, and kinetic friction while the object is moving. So the coefficient of friction actually depends on the type of the material that it's sliding on and the condition, whether it's wet, dry, But it
Usually the
doesn't
problem will
matter.
specify.
It will specify. It usually gives you the coefficient of friction too. but it does not depend on the contact area of the object. So it could be sliding, you know, horizontally or like at an angle, but it'll still have the same like coefficient of friction. And so with friction, there's 4 like conditions you could say. So there's the first one where like there's a force that is perpendicular to the object and it's not really acting on it too much. So there's no friction on it. Second one is like there's a bit of a force on it, which it's still not moving it, it's still being applied. But the third one is right before, like the instant before it starts to move, we still have static friction. And this fourth condition is like when there's enough force to move it, to overcome that static friction, then it has the kinetic friction.
So the friction kind of like increases as the force increases, but only up to a certain point.
That's true. There's a maximum friction, which is this, the static friction.
Yeah, yeah.
And then you go into kinetic.
Usually that's probably what they'll give you.
That is
I feel
true.
like. But there
Depends
is
on
like,
the type of problem.
Yeah,
They usually
exactly.
specify with friction. But
Yeah. Yeah, beautiful.
All right, I'll see you again soon.
Move it along, move it along. What do we got? What do we got? Back to Fogel, look at him.
Back so soon? Was he that bad?
Here we go.
Come on.
Here we go.
Let me tell you about centroids. So basically, I got some definitions to start off. We got the center of gravity, which is where the resultant weight is located, center of mass, where the mass is all concentrated, and the centroid, which is the geometric center of the body, like the physical center of it. So we just want to locate them essentially. We have 2 ways of doing that. If you got some like weird shape that doesn't really follow any like area formula, you can integrate it with its function. This is the formula for that. Pretty straightforward, it's just integration.
There's some glare.
We gotta come.
Here we go.
You can also, if we have areas that make sense like this, where it's a half circle and a square cut out of it, you can do the composite bodies way of doing it. So we're solving for center with respect to x and y. These are the equations for it. These x bar values are given, and these ones that we found down here, those are from formulas that are given. They'll probably be on the equation sheet. I hope to God they are.
Little hint there. Into that something.
So right now, all we have to do, it's pretty easy. We're just gonna find the areas of these 2 shapes. We're cutting this out, so we're gonna be subtracting it in the end. So the half circle, 2200, closer to 2300. This box, 320. The sum of the area, down here. I'm gonna subtract the 2, we get 1948. These 4 values are all found from a table. Can't really show you the table, it's scary stuff.
Will that table be given on the exam?
I really hope so. If you're
What's on the table? So the equation to find
the equations to find these x bar, y bar values.
gotcha.
Yeah, you just plug in like the length and area values that you get.
Yeah.
It's
Some of
simple.
them it's kind of intuitive. Like if you're looking at a square rectangle.
Yeah, if you're looking at a square,
it's gonna be.
I don't even know if they
I
provide
think
one.
the only one I've memorized is the triangle.
right
where it's like-
triangle?
Yeah,
1/3.
1/3 from the right
The
corner.
yeah.
Yeah.
But you're saying you really, really hope that they give it to
I
us.
really hope. Like I would be like super grateful. I'd come to office hours more often.
Weren't you also
know.
talking about like you're really hoping we get some extra credit too?
Oh my god, dude, thank you. I
Yeah,
almost
yeah,
forgot. You know, extra credit's like a great thing.
I mean,
Just give me like 50% extra credit, we'll be good.
give me 60.
60.
As
Yeah.
a test to see if TAs are actually watching this, give us like 3 points extra credit, and then we'll know if you actually saw
I feel
it.
like three extra credit points. We're not gonna know. Make it like something significant.
Okay, let's
All right. Back to
kidding,
this
just
formula.
kidding.
We're just summing everything up. So we're gonna multiply, sum it up, divide it by our summed area. That's all. All right. Come here.
Oh, we got Andrew teaching. Look at this. Taking us on a little journey here.
All right.
What are we learning
You know about a
today?
little distributed load. Evan's got a few of those. Okay, so it's gonna look like this. It's gonna have a distributed load across a beam or something like that. So the number one thing you're gonna do is we're gonna use centroids of what Evan just taught us how to do. We're gonna be replacing the distributed load. So we're gonna replace all of this with a concentrated load to simplify it. So I've replaced them with these 2 vectors here. And now you may be asking, well, how do I know? Like, how'd you do that?
How'd you do that?
What happened
What you
there?
doing?
So, the magnitude, as we've gone over before, is going to be your area under the curve. So the magnitude of, like, let's say this vector, what I've gone here is separated this triangle into 2 triangles, 2 right triangles. So it's going to be this vector is going to be representative of all this area, and this vector is going to be representative of all this area. And so the magnitude of this vector is going to be the area of this.
So I gave, let's say the height was x. This is really poorly drawn, not representative. The height was x, and the length was y. We'd split this up, and you'd find the area of this, and that would be your magnitude. And then the location, as Evan was saying, the line of action of this vector, same thing as like where you're going to put it, the location, is going to be your centroid. So like I was saying, it's going to be 1/3 of the triangle from the right corner. So if the right corner is here, let's say this is 6 units long, our centroid is going to be 2 units from the right corner. So it's going to be like right here, which is why I've drawn it right here. And so that's really how you combine a distributed load and simplify it. And then you can solve it. And usually you'll probably solve for another unknown or something. It's usually going to be an equilibrium. But I think we can go ahead and move on to lecture 16.
I'm so excited. Dude, still.
All right, moment of inertia. It builds off centroid. So a lot of this you already know if you were listening.
Do you want to share, Thomas?
Similar formulas, we're still integrating. A big part of this is really just deciding if you're gonna integrate with respect to x or y. A definition is that moment of inertia is the measure of a body's resistance to bending or rotation. A little cool thing is that the higher the moment of inertia, the lower the stress in its body. So another procedure, decide if you're gonna integrate horizontally or vertically. Set up your integration, integrate, easy stuff. A little extra thing is the parallel axis theorem, which defines that the moment of inertia of an object is equal to the moment of inertia about a parallel axis. These are the equations. You will do ix tilde plus a dy squared, where dy is the change in y. I have it. I wrote it twice. I think this one's changed in y. And then for y, it's the same thing, just with flip bounds.
I think something important to note, if you're integrating with respect to x, let's say we're trying to find ix, you're usually going to want to integrate horizontally. So that's just something that
I
she
took a
talked
note of
about.
that over there.
Oh, there we go. Thank you.
Forgot, just put it off on the side.
Yeah, so typically, I mean, you could do vertically. Typically the way that the integration works out, you're going to end up having a lot easier time doing it horizontally. And then for y, you're going to do vertically, as Evan has pointed out right here. But yeah, are we ready for 17?
I think I'm ready.
Final. Who's
Come over here. Come over.
Professor Rowan, once again.
We're fine. I think we're finally done with him. Finally.
Thank God.
Okay. Whew. Let's see what we got here. Okay. We have rectilinear versus curvilinear motion. Do you want to check?
You got my.
It's for me.
Yeah, no, that's for Tom.
Don't stand on rolling chairs. It's not safe.
Only. So we have rectilinear versus curvilinear motion, correct? So rectilinear is kinematics along a straight line, right? While curvilinear intuitively is around a curve. So with both, we actually have position, which is location of a particle. You should know this stuff, but just going over it again. Velocity is the speed or the change of position of a particle over time, while acceleration is how much that velocity is changing. Change in velocity over time. So I'm gonna go over what's it called? Relative velocity. Yeah. So we have a fixed observer here, right? Looking at a moving observer A over there, and we have the point B that they're both referencing. Oh shit! Yeah.
Do you need four?
Yeah. Okay, that's good. Yeah. Thank you. So we see that the fixed observer sees point B along this line and sees point A along that line. But we want to see how the fixed observer observes point B with reference to A, correct? Which is RBA. And if we know RB and RA, we can actually see that the reference velocity that the observer sees is RB minus RA. Very important. And then shifting back to rectilinear motion, we have 3 very important equations for kinematics. We can derive all of them. I don't know if I want to go through every derivation.
I think we're given the final.
Yeah.
things on the
There's a
test, but
derivation here, but I do not want to go over that.
Yeah.
So we have.
We've all seen these before.
Yeah. I mean, if you're in this class, I would very well hope that you've used these before. But I'll still test you on it later. So curvilinear motion is what's like the new addition to this class, kinda. So we have this interesting diagram here, where we have the origin, right? This is where you know, the origin is, we have an R and an R prime, which is like, if you're moving along a curved path, you have two different reference points to where you start and where you finish. And the change in that R is your position, is that your displacement from where you moved along the curve. So with curvilinear motion, we actually have two new axes. We have the n-axis right here, which is perpendicular to the path you're moving along. We have the t-axis, which is tangent to the path. And we have rho, which is the radius of curvature, which is the distance from the curve to the origin. If you can see it right there. Finally, let me step down. Finally, we actually have acceleration. This is like an interesting way to look at it with curvilinear motion. Since I just talked about the n and the t-axis, we have an n component of that acceleration, or centripetal, which is given by b squared over r. It's directed at the center, towards the center of the curve, while the tangential component is on the t-axis, which is in the direction of the velocity. To find the actual magnitude of acceleration, we take the magnitude, or the norm, of both of those components. Sweet. Right. I'll let Andrew take it from me.
And this is going to be some kinetics. So when you're dealing with these type of problems, this is the first time where your delta F is not going to be 0. So the sum of your forces is not 0. So it's important to keep in mind, it's now going to be F equals ma. You've definitely seen this equation before, but you haven't applied it in this way. So if we have a box, there's a hill right here. This box is on the hill. We're going to go ahead and draw the FBD, which we've all done before, but now we're going to add on the KD, which is our kinetic diagram. So your kinetic diagram has the accelerations in each of your axes. And there's now a lot of different ways to represent your axes, as Case just talked about. We also have the tangential and the norm. So you can also see that right here. I have 3 different diagrams. This is kind of what Case was talking about, but you can see, depending on where this is on the homework, this is the coaster problem. Depending where the where the coaster is on the track is where your normal acceleration is going to be pointing. So it's pointing towards the center. This is a circle radius 5, circle radius 10, pointing towards the center. But here it's decelerating, so the tangential is always going to be pointing this way. And then these are, Case talked about these as well. But in these types of problems, you're going to have your acceleration, your kinetic diagram, and then your FBD. And usually you can go ahead and isolate these two, solve for your total accelerations, given that like you're usually given the mass, or the masses will sometimes cancel out. But that's going to be your typical approach for that. If you have these two drawn out correctly, the problem should be pretty straightforward, just plugging in. But the important thing to recognize is which direction your accelerations are going to go, because now it's not going to be as intuitive. You're going to have either normal acceleration towards the center, or tangential is going to be given in the problem. But yeah, so we're on to the last lecture.
Woo!
Who's still shaking it out?
Should I record
it? Yeah.
Look at that. Alright. We're almost there.
Which one's 20?
We're here. This is lecture 20. This is particle kinetics. So we're used to the standard rectangular coordinates, which you've seen in some of these, which is like kind of what you expect. Fx is equal to max, fy is may, so on. We've also learned normal tangential, which some of my colleagues have already explained. Now we're introduced to cylindrical coordinates. So just some quick stuff to know. If a particle is considered in movement to only the r theta plane in movement, I wrote that twice, then only first 2 equations will be used. And then we should also know that the fixed coordinate system used, we use the fixed coordinate system, not the body-centered, like the normal tangential approach for the cylindrical coordinates. So for our F equals ma equations, we'll see that they turn into, we'll have an FR component is equal to MAR, which is also equal to this, which should be given, hopefully. We have F theta is equal to MA theta, is this. On the notes, this sign was incorrect on one of the slides. I believe it's plus. I can't remember. I'm pretty sure it's plus. And then F of Z, it should be on the sheet. F of Z is equal to MAZ, M double dot z, and the dots you probably know by now is just derivatives. So one dot is the first derivative, two dots is the double derivative. And here we have a diagram representing these forces, which you can analyze for. You can pause the video here. Make sure you know this. You should know that for the test. And then we have an example, the last example. We were given this in class. It's got this like the slope, and then there's a ball here, and then there's this arm that's on like this pivot point here, and that's pushing up. We'll see our direction of, in these problems, there'll always be a direction of, if it's a rotation like this, will be a direction in which the theta is moving, so that's important to note. And it's pushing this ball up the hill. We have our arc component, and then for these types of problems, you probably want to do an FBD and a
KD.
and a KD. I didn't label it. A
Kinetic
KD,
diagram.
Kinetic diagram, which Andrew talked about earlier. This would be the free body diagram of the can. This would be the kinetic diagram of the can. And then in this problem, we were solving for n and prime. But
Thank you very much.
yeah, it's 20
I
chapters.
think that's all 20, yeah.
You're gonna pass your final.
Wow.
That was a great quarter.
That's it. What if we deleted the video and redid it?
Thank you.
All right, thank you for watching.
So, yeah,
Try to hide. All right. Dude, this is taking up way too much storage.